Welcome back to Quantitative Chemistry, and this is our final section of this topic, you'll be glad to hear. And actually it's not a very difficult part of this topic. We're going to be looking at something called percentage yield. So if you look at page 2 with me, at the top of page 2 we have these 2 points of the specification, 1.7.6 and 1.7.7. We're going to be doing both of these in this video, but it won't take us too long. It's looking at what might stop a reaction from going to completion and us getting 100% yield in terms of the amount of product that we form. And actually calculating, well, what is the percentage yield? What percentage of product did I get compared to what I might have expected? So we're going to be starting on page 26. So we're going to try to fire through this quite quickly because you've had some long videos for this topic and there's not very much to this. So this idea of percentage yield, essentially it's a measure of how productive our reaction is as such. Because what we have assumed in our calculations so far is that 100% of our reactants are converted into products. Let's go back to that equation we keep referring to, magnesium reacting with oxygen to form magnesium oxide. So what we've essentially assumed so far is that if we relate it to this example, all the magnesium reacts with oxygen completely to form the maximum amount of magnesium oxide. But in fact, a 100% conversion of reactants into useful products is very, very rare. And this is a really common question. It asks you, well, why do we not see a 100% yield? Why do we see that the yield is less than 100% for most reactions, that in fact not all of our reactants are converted into products? So for a 100% conversion, you have to have all of your reactants forming useful products. So here are some reasons that you need to learn, and this is quite often either a 1, 2 or 3 mark question. They'll either ask you for 1, 2 or 3 of these reasons. So they may say, give 2 reasons why a 100% yield may not be seen. So reason number 1 is that we can have loss of product and separation from the reaction mixture. So in other words, if I am doing a reaction in, let's say, a conical flask, and I'm trying to extract my product at the end, some of my product may be left behind in the conical flask. I might not get all of it out. But also, if we were transferring our reactants from one apparatus to another, so say for example, I am carrying out an experiment and the first part of my reaction is in a conical flask. And then I have to do something else to it. The second stage I carry out in a round bottom flask, and then I transfer that into a beaker to carry out my final stage of the reaction. As I transfer from my conical flask into my round bottom flask into my beaker, it's likely that I will lose some of the product and also some of the reactants if it hasn't fully reacted by that stage when I'm transferring between the apparatus. That's similar to this first reason. So either we can have loss of product and separation from the reaction mixture, so we may not get all of our product from our reaction mixture. Some may be left behind in the apparatus, but also if you have this reaction mixture where you have a mixture of unreacted reactants and products, actually just getting your product out can be very difficult. Or if we have different stages in our experiment and we're transferring the reactants between different pieces of apparatus, we may lose product when we are transferring. So you can say loss of product and separation from the reaction mixture, or loss of product and transfer between our apparatus. The second thing that might happen is something called side reactions. So essentially, if you are trying to go from A plus B to C plus D, but then a little bit of the C that you have formed might then go off and react with B and form some sort of product E. I'm just giving you a totally random example here, but that's what we would call a side reaction. If one of your product then goes and maybe reacts with one of the reactants or one of the other products that you have formed, that's what we would call a side reaction. So some of the reactants may take part in a different reaction to the desired ones. So essentially all you would need to write there is side reactions could happen. And what you can see there is, in the example I've used, the general example, C has now been used up in reacting with a little bit of B. So actually the amount of C in my reaction flask is dropping. So my yield is dropping from 100% just down and down and down as that side reaction is happening. And then finally, the third one you need to learn is reversible reactions. So there are reactions which we'll study in more depth next year that are called reversible reactions. I'll show you the equation of reversible reactions. Again, I'll keep it general. So if we had reactants A plus B, they reacted together to give C plus D. But if C plus D could then react together to give A plus B, again, we would call that reversible. So you can see here, my arrow represents that my reaction is going in both ways. So you can see there the arrow I've drawn red, that's the forward reaction, A plus B giving us C plus D. But the arrow I've drawn now in green, that's the backwards reaction. So that is C plus D reacting to give A plus B. You don't need to worry too much about that. For now, we'll look at that in more depth next year. But you can see how that would cause our yield to fall below 100%, because once our products are formed, they can react together then to give the original reactants again. So I'm not getting as much product formed as in an irreversible reaction, one that goes in the forward direction only. So 3 reasons why we might see a percentage yield of less than 100%, loss of product in separation from the reaction mixture or in transfer between the apparatus, side reactions and reversible reactions. And again, a really common exam question, so make sure you learn these. So now we're going to move on and look at how we actually calculate percentage yield. So in the moles calculations we have been doing so far, essentially what we've been calculating is the mass of product that we would expect to obtain based on the mass of reactants that we used. So again, let's go back to that equation of magnesium reacting with oxygen. If I had worked out that I had 5 moles of magnesium and I wanted to work out how many moles of magnesium oxide I would expect from this reaction, I would bring it across. My ratio of my balancing numbers, you can see, is 2 to 2, which is the same thing as saying 1 to 1. So 2 to 2, which is 1 to 1. Okay, so 5 essentially divided by 1 times by 1, I'm going to get 5 moles of magnesium oxide. And what I'm essentially saying here when I bring that number of moles of magnesium over to magnesium oxide, essentially I'm saying that I expect all 5 moles of magnesium to be converted into magnesium oxide. I expect a 100% yield. But as we've just seen, there's many reasons why some of that magnesium may not be converted into magnesium oxide. So what we're saying here, the 5 moles of magnesium oxide that I expect to form is something called the theoretical yield. The theoretical yield, which I'll highlight here. So when we've been doing our calculations previously, the number of moles that we bring over to our product, that's essentially our theoretical yield. What we're saying is this is the number of moles of product that I would expect to form if there was a 100% yield, if 100% of my reactants were converted into products, if there were no side reactions, if there were no reversible reactions, if there were no loss of product along the way. That's what we call our theoretical yield. So this 5 moles that we've brought over, that's our theoretical yield. Now that's it in moles. We'd have to go and calculate the mass of it, but we'll not take time to do that now. But as we have discussed, there are many reasons why there would not be a 100% yield, why we might not get 5 moles of magnesium oxide actually produced. And so what we can do when we've carried out a reaction, we can weigh or take the mass of the product that we actually form, and that is what we call our actual yield. So the actual amount of product that we get is what we call the actual yield. So just as the name suggests, the actual yield is how much we actually get. The theoretical yield is how much we would expect to get in theory if the conversion was 100%. And then to work out the percentage yield, we've got a very, very simple calculation. To work out the percentage yield, you simply take your actual yield you divide that by the theoretical yield, and you times by 100%. So make sure you write that in, and make sure you write it in accurately in that box. Because sometimes in past paper questions they've asked you just to write the equation. They haven't even asked you to do a calculation. They've just asked for the calculation to work out what the percentage yield would be. So say for example, I had worked out that my theoretical yield in a reaction was 20 grams. Okay, so I'd done my moles calculations and I'd worked out that in theory I was supposed to get 20 grams, but my actual yield was 5 grams. I'm just making up values here just to show you this in action. So if I want to calculate my percentage yield for this reaction, what I would be doing is taking my actual yield, which is 5 grams, dividing that by the theoretical yield, which is 20 grams, and timesing by 100%, just to convert it into a percentage rather than a decimal. Okay, so actual yield as a percentage of your theoretical yield. That's essentially all we're doing. So 5 divided by 20 times by 100 is going to be 25%. So you can see here my percentage yield is 25%. 25% of my reactants have been converted into products. You can see that only a quarter of what I was expecting to actually form. One thing to notice with this, the only thing that could possibly trick you with this is getting the actual yield and the theoretical yield the wrong way round. But one thing to always remember with this is that your percentage yield should always be less than 100%. Always be less than 100%, because if you've got it over 100%, then what you're saying is that your reaction is forming more products than you actually expected to. It's forming more products than you have reactants to actually make. It's almost as if you were making a cake and you had enough ingredients to make one cake, and actually when you took it out of the oven there were 2 cakes. That's impossible because you don't have enough ingredients to make 2 cakes. You didn't put enough ingredients in to make that amount. So your final percentage yield should always be less than 100%. So that's something to check with your answer. There's one last thing that I want to point out. You need to make sure that your units are the same for your actual yield and your theoretical yield. So you can see here that my units were in grams. So I had 5 grams of an actual yield and 20 grams of a theoretical yield. So you can see when we did our calculation that those units essentially cancelled out with each other. But say for example, you were given an actual yield of 850 grams and a theoretical yield of 1 kilogram. You can't just put that straight into the equation because your units won't cancel out. And if you think about it, if we were to put it into our equation, we would be doing 850 over 1 kilogram times by 100%. 850 divided by 1 would be 850 times by 100. We'd actually have a percentage yield of 85,000%. That does not work. That is not what happens here. So what do we need to do? We need to convert one of these masses into the other unit. So either you need to change your grams into kilograms or your kilograms into grams. I think it's probably easier to convert from kilograms into grams. So what you might say is that actually my theoretical yield is 1 kilogram. To convert that into grams, I multiply by 1,000. So my theoretical yield is 1,000 grams. So then I put it into my equation. My equation then would be 850 over 1,000 grams. You can see now that they're both in grams. Times by 100%. And you would get 85% for that. So what I'd like you to do somewhere on your page is to write yourself a wee note. Somewhere on your page, doesn't really matter where, wherever you have room, maybe beside the box where we've written our equation, could you write yourself a note to check that your units of your actual yield and theoretical yield are the same. Okay, so check the units of your actual units and the theoretical units are the same. So if one is in grams and the other is in kilograms, you need to convert one of them so that they're both in the same units. So what I would like you to do is in your blue books to try these calculations. So take a title of percentage yield, and you can see there's a 1 in brackets there. There is one more exercise to do, but that's just putting our moles calculations and percentage yield together. So these ones are very, very simple. It's just using that equation that we've just looked at. So I'll show you for number 1. And again, I'd like you to show all your working out. So in number 1, A, you have been told in a reaction to produce paracetamol, the theoretical yield was 200 grams, but the actual yield was 150 grams. So it's just about making sure that you get these the right way around. So what I would do, as I did on the previous page, is highlight the theoretical yield in one colour, and you can even just highlight the value if you want. And the actual yield was 150 grams. So it's just about making sure you get that the right way around. In the exam, always make sure that you write your equation out. Sometimes you get a mark for that, so make sure you write the equation out first, and that also makes sure you get it the right way around as well. So the percentage yield is equal to your actual yield over your theoretical yield. I want to see that equation written out for each of these calculations on this page, and then you multiply by 100%. So our actual yield is 150 grams. Our theoretical yield is 200 grams. And then we multiply by 100%. If you put that into your calculator, then your final answer should be 75%. And as you can see, I have given you the final answer for each of these to make sure that you've done it right. If you don't get the same answer, then look to see what you have done wrong. So what I'd like you to do is pause the video now, try these 4 questions, and then we'll move on to the last section of this topic, which is essentially just putting moles calculations and percentage yield together. So the last thing we're going to do is to put our moles calculations and our percentage yield calculations together. We're not learning anything new. You've essentially covered the whole topic at this stage, but it's just putting these moles calculations and percentage yield calculations together, because you could be asked percentage yield as part of a bigger moles question from the mass of a reactant. Now the good news is up to now, if they've ever asked you to do this together, there's been a part A and part B question, which is the format that I've kept all these questions in, the example questions in your notes. It just helps break it up a little bit, but essentially what we're doing is we're doing 2 stages. The first stage is to use our normal moles calculations, either our reacting mass calculations, or if you're given the mass of 2 of your reactants, you'll need to use limiting reactant moles calculations. So you can make a note that that's what we mean there, but you'll see that in the examples. And the value that gives us is the theoretical yield. So our normal moles calculations ask us essentially to calculate the mass of product that we would expect to be formed. Or you may have noticed in previous examples, they've talked about calculate the maximum mass of such and such that can be formed. And essentially, maximum mass is the theoretical yield. And then in the second part of the question, you will be given a value for actual yield. And from that, you can calculate your percentage yield. So it's a 2-part question using your normal moles to work out the theoretical yield, and use the equation for percentage yield to then calculate that percentage yield. And for that, you will be given a value of the actual yield, because you can't know that from your calculations. You will be told, say for example 10 grams were actually obtained, what is the percentage yield? So that second part of the question is just the simple use of the equation. So I'm going to take you through one example and then let you try a few yourself. So let's read through the worked example together. So it says 14.8 grams of butane 1-ol. You're given the formula and the RMM, which is just the same as RFM. were converted to 1-bromobutane, again you're given the formula and the RFM, by refluxing with sodium bromide and concentrated sulfuric acid. Part A of the question asks you to calculate the mass of 1-bromobutane that could be obtained. And essentially what you're doing in part A is using our normal moles calculations to work out the theoretical yield. So let's do a recap of how we do that. So thinking back to our moles calculations, our first step was to write the information we know underneath the equation. So I have rewritten my equation to make that a little bit easier, and then I'm going to highlight the information that I have been given. So I've been told at the very start of the question 14.8 grams of butan-1-ol C4H9OH. So if you weren't sure what butan-1-ol was, which is fine at this stage, you won't really know what that type of molecule is until next year when we look at organic chemistry, but you're given the formula there to match it up with. So I'm writing 14.8 grams underneath that reactant. You'll notice that I haven't been given any other masses, and so that tells me that this is not a limiting reactant calculation because I haven't been given a mass of my hydrogen bromide. And so it is just my reacting mass calculations. I only need to work out the number of moles of one of the reactant because that's all I've been given. What am I trying to work out? Well, the question asks me to calculate the mass of 1-bromobutane that could be obtained. So it's a product because it says the mass of 1-bromobutane that could be obtained. So if you want to write that, that's a product. So if you look at your two products, you've got C4H9Br and you've got H2O. Well, we know that H2O is water, so C4H9Br must be 1-bromobutane. But you can also see from our question, the start of the question, it says it was converted to 1-bromobutane C4H9Br, so you can match it up with the formula there. What we also write underneath our equation are Rfm values. So you can see the Rfm of butan-1-ol is 74 and of 1-bromobutane is 137. So make sure you get those the right way around. So for butan-1-ol, the Rfm is 74, and for 1-bromobutane, the Rfm is 137. Okay, so reminder of what we were trying to do. Part A, calculate the mass of 1-bromobutane that could be obtained. So what I need to do is work out my number of moles that I have of butan-1-ol and bring that over. Because remember, we can only transfer the number of moles over. So N equals mass over Rfm. You should be very familiar with that equation by now. Our mass is 14.8. Our Rfm is 74. Put that into your calculator. Take a second and do that. And that should give you a number of moles of 0.2 moles. Again, because we weren't given the value of the mass of hydrogen bromide, then I don't need to work out its number of moles. I can't because I don't have a mass. So I'm just bringing this over. So that's my number of moles. I bring it over to the 1-bromobutane. And I need to think about my ratio. So look at the balancing numbers in front. You can see that in this equation there are no balancing numbers. So essentially our ratio here is 1:1. So that means I'm going to form a maximum of 0.2 moles of 1-bromobutane. Remember that just as we've discussed, essentially this is your theoretical number of moles of 1-bromobutane that we would be producing. If all of my butan-1-ol is converted into bromobutane, then I would get 0.2 moles, and we'll take that into consideration in a second. So again, part A asks us to calculate the mass of 1-bromobutane. So I now need to use my equation. Mass equals N times Rfm. My number of moles is 0.2. My Rfm is 137. Again, put that into your calculator and you should get 27.4 grams. Okay, remember to put your units at the end. Now let's think for a second, what is that value? What is that mass value? Well, again, look at the question and that gives you a clue as well. Part A says, calculate the mass of 1-bromobutane that could be obtained. I'm going to highlight that word could in blue for a second. Calculate the mass of 1-bromobutane that could be obtained. Essentially what part A is asking you to calculate is your theoretical yield, and we do that by using our normal moles calculations. Our normal moles calculations tells us the maximum mass of product that we can form from a reaction if all of our reactant converts into product, and that would be assuming a 100% yield, which we know in reality doesn't often happen. So your value of 27.4 grams, I want you to either highlight that or circle that. And I'm keeping this consistent with my colours up above in the steps. This value is your theoretical yield. What you've just calculated in part A is going to be the theoretical yield for our percentage yield calculation. So hopefully that makes sense. Most calculations give you the theoretical yield. In theory, how much could I produce? And then part B says 17.8 grams of 1-bromobutane were actually obtained. What is the percentage yield? And this is where we need to use our equation for percentage yield. But what value are they giving us here? 17.8 grams of 1-bromobutane were actually obtained. Now, they don't always use that word actually, but that's a big clue. What value is this? Either circle it or highlight it in the same colours as we did above. That is our actual yield. That's the value for the actual yield. So if we then write down below, part B, we're simply calculating our percentage yield. Percentage yield, we need to remember our equation, is actual yield divided by our theoretical yield times by 100%. So in this example, our actual yield was 17.8 grams from up above here, our 17.8 grams. Our theoretical yield, we calculated in part A, was 27.4 grams. And you can see they're both in grams, so we don't need to do any converting here. But don't forget to multiply by 100%, otherwise you'll just get a decimal value of less than 1. Put that into your calculator and you should get a value of 65.0%. If you put that into your calculator along with me there, you should have got 64.9635, but generally round these answers to 1 decimal place. Generally round the percentage yield values to 1 decimal place. So that's how you put the two types of calculations together, your reacting mass or limiting reactant moles calculations. That gives you your theoretical yield, and then they will give you an actual yield and ask you to work out a percentage yield value from that. So that's if they're putting those two types together. But they'll always get you to calculate the theoretical yield first, although they might not call it that. They might say, as it did in this question, calculate the mass that could be obtained. And then they'll give you an actual yield for you to calculate the percentage yield. So what we've got in the next couple of pages is some examples for you to try. So let's take a look at those now. So over on page 29, you have the start of these questions, and as you can see, as I've done before, I've given you the final answer so that you can check before you move on. So you can see here in question 1, it says, what is the maximum mass of ammonium chloride that could be formed? And it gives you the masses and so on. So the maximum mass, essentially in part A, and it will be the same for each of these questions, in part A, you'll be calculating the theoretical yield by doing a moles calculation. Okay. And then in the second part, it says this experiment produced only 8.3 grams of ammonium chloride. I'll highlight that in pink. That's your actual yield. So in part A, you'll be calculating the theoretical yield. Part B, you're given the actual yield and you're asked to work out the percentage yield. Using your equation, percentage yield is equal to your actual yield. I'm just abbreviating it here, but you should write it out fully, over your theoretical yield times by 100%. And that's the exact same for each and every one of these questions. If you turn over the page with me, I just want to point one thing out about question 5. So question 5 here, it says iron can be formed from iron oxide using carbon as a reducing agent. You're given the equation, and it says here a mixture of 24 grams of iron oxide and 3 grams of carbon were mixed. So you've been given the mass of iron oxide and of carbon. So what do you need to do? This is a limiting reactant type of example. So you need to work out your limiting reactant first. So you're going to need to calculate the number of moles of iron oxide and calculate the number of moles of carbon. Remember to divide by your balancing number. So divide your value of iron oxide moles by 2, your value of carbon moles by 3, and use that to determine what you're bringing over to your iron. So just be really careful with this. It might be worthwhile looking back at your limiting reactant calculations before you do this one to make sure you're confident in doing that, because there is that little extra step with the limiting reactant. But other than that, these questions are all the same. Doing your moles calculations to get your theoretical yield, and then part B will be calculating your percentage yield using the actual yield that they give you and the theoretical yield that you've calculated in part A. So again, set these out in your blue book and take your title of percentage yield 2. And make sure you show all your working out. So your moles calculations in part A of each of these questions should be completed underneath the balance symbol equation. And then for part B, when you're calculating your percentage yield, make sure you write out the full equation for percentage yield, as in percentage yield equals actual yield over theoretical yield times by 100%, and then put in your values after that. So show all your working out. Don't be taking shortcuts. You need to learn how to do these properly, because it will stick with you far longer if you actually do your working out, and you need to be able to do these under exam conditions. So take some time, do those calculations now, check that your answers match the final answer which have been given to you in brackets after each of the questions. If they don't match, you've gone wrong somewhere. Try to find the problem yourself first of all, and if you're struggling to find where you've gone wrong, then get in touch.